So like, you know, if you have to check your notes or if you go to YouTube to check a video, you know. Yeah, I think so. Okay, let's continue. Alright, we're starting now. Listen, I'm Jed. Listen, thank you. Right, so we're having a look, I think, at the next section, which is rules of logs, because last time we did rules of indices. And some people actually are familiar with logs already. So let's have a look here. Firstly, we should start off with the definition of log. So we have, usually logs written like this, log, and a number here, and a number here. And this part is the log, we call the base, and this part here I would call it the argument, or the variable, or the input, or whatever. And the meaning of log is this. So if you have log with a number and a number here, we kind of think of it as meaning this question. You ask yourself, 2 to what power gives 8? Yeah. So whatever number you can imagine goes here to make the answer, that's what we say this is equal to. Yeah, so it's kind of like a question. You know, if I wrote here log 525, it's like asking you, what power do I put on the 5 to make it 25? Like, how do I raise the 5 to what power to make it 25? So in this case, obviously, it's 2. Argument, yeah. A variable, input, whatever. Yeah, yeah. You know this word, don't you? No? Yeah, same word. Yeah. Okay. This is the basic concept of log. So let's just try and do some together. Enjoying those? You're not going to give me one? I'm quite hungry now, you see, because I've been teaching both the weak and the strong students all morning. I had both groups, you see. I know, it's okay. This should keep me going. Who knows?
We know.
Or maybe I had the strong ones first, and when I have more energy, I have the weak ones. Or maybe I'm talking to the weak one right now. Okay. So, let's just practice some numbers. For example, log 10 100. What's that one? 2. Yeah, 2. Log 5 125. 3. Log 2 1024. The 10. 2, 4, 8, 16, 32, 64, 120, 256, 5, 12, 10. Wonderful. Okay. Log 5 1. 0. Okay, so there's some few examples to get us started, and now we'll look at something a little bit harder. So you can just write these 4 down. One step at a time. Not that one, no. Oh. Okay. We got that? Yep. So, last time we did rules of powers, and likewise we'll have rules of logs. So let's look at the rules. Okay, so rule 1. So if you have a log with a base of two numbers which are multiplied, so x times y, that will be the same as if you got the log of each number separately and added them together. Now you can see this as an example, okay? Watch. Log base 2, and we'll say 32. Okay? Now what two numbers make 32? You could say 16 and 2, so that's log 2 16 plus log 2 2. Now let's see if that checks out. 2 to what power makes 32? 2, 4, 8, 5. 2 to what power makes 16? That's 4. And 2 what power makes 2? Yeah. So I mean it's true. It is true. So what we need to do now actually then is the proof. Okay, so the proof will start off by saying let x equal b to some power, and let y equal b to some power. Now we don't know what these numbers are, but it's possible to do. Like what we did in the previous example, you know, for example here, if x was 16, then we could say 16 is 2 power 4. Anyways, log bx y, so I just replaced x and y. X and y gets replaced with these two b's here. That's equal to log b n plus m. Now, this is kind of obvious if you think about it. B to what power will make b power n plus m?
But must be m be the
Wait, yeah.
must be m be the other plus y?
Which one? Here?
I mean, like you can close the b with the b.
Close the b with the b.
Still like divide b by b, right?
No. She can tell me what she means. Go on.
You can close the b and the b.
Now, there's many b's here. Which one should I be looking at?
Must be
This
the
one.
one on the right.
This one.
Yes.
Yep.
It can go with the other because the other.
These.
Yeah, I mean yes, you can close them because they are the same.
I think I know what you mean, but I'm not so sure. I can close them? Cross them? Ah, you mean cancel them?
Yes. And then maybe
Kind of, yeah.
well.
Yeah, kind of cancel them. It's like a cancelling, yeah. This is equal to n plus m. Yes. I wouldn't quite use the word cancel, but it is like a cancel, because it's as if these two are gone. But this is how I think about it. Here this is b, and here this is b n plus m. So obviously the power that I need is n plus m. Okay, so finally, n, I can change n into log bx. B to what power makes x? Well, look back here. B to what power makes x? N. So this is obviously n. And b to what power makes y? M. So I've just changed this, or I've just proved this. Because remember, this guy here was originally log xy, just replaced. So I've shown log xy is the same as log x plus log y. Okay, so that's the first one proven. Because students have trouble with logs, I think it's good if you write this proof down, because a lot of students have real trouble manipulating logs sometimes. So I think it's good to have in your notebook. You can write this down. Did you write this down, Amjad? Okay. Don't worry, I'm just getting myself ready. Rule 2.
Would we be asked to prove?
No, but logs is something that students find hard. So I want you to have more notes in your notebook. Okay, the next rule, I'll just write it down. I think it's a rule you might already know. Log b x over y is equal to log b x plus y, yeah. And the proof is nearly the same. So if I go back to my first proof, all I do, instead of x times y, it's x divide y. I want to prove that it's equal to minus here. So, it's the same thing, yeah, bn, bm. So here this is divide, here this is divide, here, yeah, up the top now is minus, because it's bn divided by bm is bn minus m. So this is a minus, so this is a minus. So the proof is the same really. It's just C proof 1. Rule 3. Okay. Yeah. Rule 3 says log b x power n is equal to n log b x. Effectively saying that powers can be brought down in front. Okay, so the proof. So, log b x n equals log b x times x times x n times. But according to the first rule, I can change this into a sum. I can say it's log b x plus log b x plus etc. by just using the first rule. How many of these logs do I have? N of them. And they're all the same, yeah? So it's just n log b x. That's the end of that proof. Okay, did you write this one down? No? The proofs you don't need for the exam, but they're very useful for your understanding and practice and manipulation of logs.
Honestly, the formula is just simple and the proof is just making it.
But these proofs aren't too hard though. Like this one is just me using rule 1. That's all. Okay. Okay. I can scroll down a little bit, like here. Rule 4. We'll go with log xy. I just changed the letters, not a big deal. That's the same thing as 1 over log yx. So what I'm saying in effect is, if I ever swap the base in the argument, yeah, reciprocal is the price I pay for doing that. So, something like log 8(2) is equal to 1 over log 2(8). Yeah. Now this actually is a very useful rule, because sometimes there's something that you want that's in the base and you need to get it out of the base. So you can use this rule to flip it out of the base. It's kind of a common situation to find yourself needing this rule. That you have a thing in a base, you want to get it out of the base, so you flip it around like this. Yeah. Okay, so let's have a look at the proof here. I think what I'll do is, I'll do something similar to the first proof. I'll say x equals bn and y equals bm. Same kind of idea. So this becomes log xy equals log bn and bm. Now this actually, you can figure out, if you think about it for a moment, what must this equal? So bn to what power will make bm? I think some of you can figure this out. What power goes on bn to make it become bm?
M minus
Yeah, so what will I put?
N by M?
Now, are you using Irish or British by?
British.
No, translate it for me, please. Give me a different word.
multiply n.
Yes. Yeah. Or we could just say more easily m over n. Yeah. Yeah. Because think about it. If you have bn and you use this power, what do you get? bm. Yeah. Okay. Right, so that's okay. Now, what I can do is I can change this into 1 over n over m. That's actually the same thing. Like if you have 2 over 3, that's the same as 1 over 3 over 2. And you can actually test this on your calculator. You might say, well, why do I do that? Well, what I can do is, I realize that this is kind of the same as this, except just that they've swapped places. So this is 1 over log bm bn, which is 1 over log yx. Okay, so that's the proof there for the fourth rule. If you can write this down, please. We think there's only 2 more to do. You wrote the proof down?
The proof is just complicated enough.
This is a lack of trust. It's a lack of trust. No, I think you should write this down.
So you're just going to confuse me.
No, you see. I don't have enough trust yet. Good. Yeah.
In the exams, is there any situation in which the article is actually prove the formula?
Not in semester 1. The only exception is they sometimes ask you that show that something is always positive or always negative. Yeah, but there's not in this sense. There's not. Okay. Do we have this rule written down?
I used to take proof of the cosine and sine of time.
Oh yeah, that's
Yeah, that's in semester 2.
Yeah, that's
in calculus.
Calculus.
Yeah.
Semester 2. Yeah. They're tricky. It's tough. Okay, we got this now? Yeah. You got that up here? Okay. Did you write all this down?
I'm still confused.
Okay, but now you have something in your notebook to look at later.
No, but I can read the rule, I understand the rule.
Fine,
This is
fine.
just confusing me. That's what's the point behind the proof. We're not
Yes.
gonna do it.
Okay, rule 5 now. Only 6. Only 6. Come on, you can live with that. If there's 10 commandments, you can live with 6 rules. Okay. Right, rule 5 now. This one actually is not used as much as the other ones. It's when you want to actually change the base to a different number. So for example, you have some base, we'll call it b, of x, and you don't want to have base b. You want a different base. Maybe you want base c. So you can't just change it into base c. There's a price you have to pay for making this change, and the price you pay is right. No, it's just a bit of a lag here. The price you pay is you have to divide by log CB. Okay? So what I mean is, for example, let's say you have log base 2 of x, and you don't want base 2. Maybe for whatever reason you want base 3. So if you were to change it into base 3, the price you pay for making that change is you have to divide this by log 3(2). Okay? So this is the price you pay for making a change of base to a number you want. Yeah? I know.
Can you put it back? Yeah.
Okay.
Yeah.
Alright, I'll remove it in a second. Sorry, a bit more. There you go. This is not really anything though.
Just an example.
With numbers, yeah, okay, yeah.
Yeah, exactly. This makes more sense than the proof.
No.
You're just adding more variables.
No. You need to practice your abstraction. Okay. Oh my goodness. Right, come on. Okay? Yes? Alright. So this proof here is a little bit tricky. If I remember what we need to do, if you look at what you have over here, you want to have C's instead of B's. So what I'll do is I'll say goodness, I don't know, I think what I need to do is I need to say let x equals Cn, and also I need to change the b. I'll say b equals Cm. Now don't write this down just yet, because I'm not 100% sure if this is the way to go about it, but we'll see what happens. So log bx equals log Cm, and on the top what do I have? Cn. What is this equal to? We kind of saw this in the last proof. N over m. Yeah. Now, n I can write as log cx, because that's what n is. C to what power makes x? N. And what could I write the bottom as? Log cb. So actually, yeah, that's the proof. Okay, not that bad. So, if you can write this down, please. Okie dokie, we got that? So the rule 6 isn't really a rule per se, it's just some special cases like log of 1 and so forth. Can I scroll down? Now, I should say, that, this, not all the rules. I mean, in some schools they have more rules, some they have less. I just find that these 5 are, enough for what you need in the exam to get by.
Have the base part.
No, you do on the Casio 991.
Yeah.
You can actually choose your base.
How do you choose your base?
I'll show you that now in a second after I do rule 6. Oh no, actually here I have the calculator open. So for example, what was the example I did earlier? Like log 2 1024. Yeah. So you type this button here. Can you see it? And then you can choose 2 here and 1024 there. Yeah. Okay. Rule 6. Not really a rule, just some statements here. So, for example, log of 1 can only ever be 0 here, yeah, because only power 0 could make the 1 that you need. Another thing here, log bx, we need x to be positive, so you could never take the log of a negative number. Like if I was to change this into minus here, I have a problem. Okay, and the other thing is, well, the problem is, well, we'll get to that now in a second. 0 here is undefined. The reason is if I typed in log 2 minus 1024, you're saying 2 to what power equals minus 1024?
To have that to them odd with them.
Hold on. There is no number I can put here to make a negative, because there's no amount of multiplying by 2 that can change a 2 into a negative.
But if it was
Yeah.
Negative base.
okay, I got it.
Yeah, negative base you could do, but we usually try to keep the bases positive.
But if the base was negative and
The
the
base
power
is
was
negative.
odd, then
Yeah, if the base
was
is negative, it's fine. But normally, it's normal to have bases as positives, and we definitely don't want to be using a base of 1. And the reason for that is this question becomes a bit meaningless, because you could say 1 to what power will make x? Well, unless x is 1, there's no number we can find. Log 110 is meaningless, because we can never put a power on 1 to make it 10. So with the exception of x equals 1, this is also not it doesn't quite make sense. Okay. Right. Yeah, but it's in the other building, so I think they must be doing drills throughout. Yeah. Undefined. Yeah.
Just a general math question.
Yeah.
Instead of expressing, let's say like if you're solving something, instead of expressing it as x is greater than 0, you also express it as x is greater than or equals to 1.
No, because we're allowed to have decimals. We could have log of 0.5. Yeah, that is allowed. Yeah,
So it's different.
it is. Yeah, it is different. Yeah. Okay, did we write this down? Yeah. Now, I need to double check it. I don't quite want to say it's a rule that the base has to be positive, but it's just unusual to have a negative base. Yeah.
Well, is it the same thing as low base 10?
Yeah, on your calculator, the default mode is base 10. Yeah. Okay.
So you can always insert 10.
Yeah, because we can use rule 5 to change a base to 10 if we like. Are we having some calculator troubles? Guys, can I just to be clear, can you look up? So some of you have this LOG button on your calculator, and it doesn't specify the base. This means base 10. So for example, what should I get here? 2. Okay. Now some of you have this button where you can specify the base. Okay. And then some of you have this button, LN. Now that's something we'll do in a little bit. Okay. We won't do it just right now. We'll do it in a few minutes. Well, does anyone know what base this is, since we're talking about it? Not 10, because the other one was 10, LOG. No.
Minus 10?
No. No. No.
I used to use it
Yes. Now, I wouldn't be particularly proud about that now. So this here should equal what? Roughly 1. Yeah. Okay, let's have a look at some examples. So the first one here, if I, where's my pen gone? Okay, if I say log 525, what's that? 2. Okay, right, next example. I want you to simplify this. Log x 35 plus log x 2. Are you sure? Yes, there you go. This is log x 70. Yeah, and you might, if you want to, you don't have to, but you might say, well, I think it's a little bit simpler to write it like this, because we don't really want to have the x in the base. I mean, but we can leave it like this. Okay, now, example. Often in the exam they give you a problem like this, and they ask you to simplify it without using the calculator. So when you're ready, we'll do this step by step here.
That 125.
Yeah, yeah. Okay, can we scroll down to this one? Right, now, first things first. When we're dealing with a log problem, we always desire to have the base the same in all the logs, which we don't have here. We have a log base 125 and we have a log base 5. So this is a problem. Secondly, we often desire the base to be smaller than the argument. So clearly, this is the guy we should target first. The base is too big and it's different to this one. What would be the easiest thing to do here? What rule number should we use? We have 2 rules to change the base. 4 or 5.
4 and 5.
Yeah. Well, which one should we use? I think 4 is a little easier, because what we can do is we can just do a swapperoo and change this to log base 5 125 by using the 4th rule. Like this now. Okay, the second thing I'll do is I will realize that 125 is actually 5 cubed. And that 125 is 5 cubed. Now, which rule should I use next? 3, yeah. So this is 6 times 1 over 3 log 5, and this is 2 times 3 log 5. Which rule next? Yeah. Which rule? Well, actually, sorry, it's not really a rule, but if I want to, rule 6 was kind of like my group of statements. So, no, I didn't actually write it down, but I'll write it down here. Log XX. What's that? 1. As a rule. It's not really a rule. Obviously, x to the power of 1 makes x. Yeah. So if I go back here, what can I do? I can cancel.
Yeah, the 6 and the 3.
No, not that cancelling just yet. Log 5 is what? 1. So it's basically that's gone. And that's gone.
And the 3.
Yeah, now let's cancel. So 6 over 3 is 2, and 2 minus 6 minus 4. Now, you can't do this in the exam, but you can at least check your answer on the calculator. So let's check it here. What's my first one? 6 log 125 5 minus 2 log 5 125. I should get minus 4. Okay, so I do. Yeah.
There's this thing that when I was trying this at home, there's this thing I figured out. It's not part of the rules, but something like, can you just follow, like I just want to explain basically.
Yeah.
If You know how we started with 6 log 1255?
Yeah.
There's this thing which I did, which is that 125, I take it to 5 raised to power 3.
Yeah, yeah,
And
yeah.
then the 3 becomes 1 over 3 to the other side.
Yeah, that's actually a rule in some books.
Oh.
Yeah. I don't want to overburden you with lots of rules, so I try to pare it back to. Obviously, if I don't have enough rules, then it makes your manipulation more difficult to do. And if I have too many rules, that's more for you to remember. So I feel like this. We see not all of these. I don't think all of these are in the book. I think the formula book might only have rule 1 and 2.
Because like in high school, when I figured this thing out,
Yeah, this is fine. I've seen this rule before.
Yeah.
It's like a rule. Yeah.
There's one rule that's called B or log B x equal x.
Yeah. Yeah, no, I know. Yeah, like B log BX is X. Yeah. We actually talked about that one later.
Oh,
Yeah.
All this to do the ln of 5 divided by 125.
You can certainly do that one at the beginning,
Yeah.
but you can't do this one at the beginning.
You can do the other one, but switch. But I mean,
Yeah, that's fine.
And log
Just
5
like with indices, there's many paths to take here. Yeah?
and log 5 or 5 over 3, you can just cancel the log 5.
Yeah.
5 over 5, so this is 3.
Yeah, you can cancel this as left with 3. This is, yeah. Like I said, there's many paths here.
But you didn't do the rule. You did the rule up.
Which rule?
Divide the rule. Log B or V over x.
It doesn't want to give too much. So that
Yeah.
so if you
That's
have it
fine.
you can use it.
That's fine. You can use it. You can use it. I'm just trying to keep a right balance between not too many and not too few. Yeah.
Why did you subtract into from 6?
Hang on. 1, 2, 3, 4, 5. Which line am I looking at? 5. Oh, why did I do this?
Yeah.
6 over 3 is 2.
Uh-huh.
And 2 times 3 is 6. Yeah. You didn't see the 3 here, was it? Yeah, okay. Right, did we write this down? Yeah? Okay, let's have a look now at ln, natural log. Can I scroll down? Yeah. So, there is an important log in maths, which is this one here. Log base e, which we did last time, x. And in fact, that's simplified as just ln of x. Yeah, or that one too, yeah. So for example, if I said, what is this, ln 3, natural log 3, that should be 1 point something. So the only way we can do this is by the calculator. So 1.099. Now you can test this out, because e to what power should equal 3? Well, apparently it's supposed to be 1.099 roughly. So if we type that in, shift, where's e here? E power 1.099, we should get roughly 3. Now, it's not exact because of rounding. Yeah. Okay, so the last thing to have a look at now is the sketch of the log graph. Can I scroll down? Not yet. Can I scroll down?
You can call it lawn.
I know, don't do that. I hate that. Yeah.
Call it lens.
I also don't like that. I don't like lin, lon, ln. No, natural log.
You want me to say natural log, Eric?
I do.
I'm used to ln.
Right. By the way, you could actually just say log, okay? Because in math class, whenever you say log, you always mean natural log. In chemistry class, whenever you say log, you always mean base 10. And in computer class, whenever you say log, you always mean base 2. So because of the context, you could just say log, and I would always understand that to mean natural log. Yeah. Right, okay. Can you scroll down? Yeah. So, let's have a look at the graph. Let's just look at simply natural log x. So, there's a couple of values we know already. What if I calculate, let's say, natural log 1? Log 1, what should that be? No?
Zero.
0. E to what power makes 1? 0. So it means here, at x is 1, I cross the x-axis. Okay? In fact, if you were to calculate some values, you'd discover the graph goes like this. It actually looks like it's leveling off as you increase here. What does it do on the left here, do you think? Mirror image, you reckon? No, not that. Opposite as in like it's increasing?
No,
Like a mirror image is what? Yeah, no, not this. What happens on the left? What happens here? No. No.
Maybe it does something.
Nothing.
Maybe it does.
Nothing. Nothing happens. Yeah. Nothing happens. Why not? Yeah, x can't be negative. X can't be negative. Remember, x can only be positive. Yes? Okay. So the only thing I want to do is, what happens if there's a number in front here? Well, if it's positive, the graph stays the same, and if it's negative, it's just upside down. So if this is if the a is positive, so actually no, I'll do it on a separate one here. So your situation is like this. If you have y equals positive number, like a positive 2 log x, then the graph looks like this, and it still crosses here at 1. Doesn't matter what this number is. And if y equals, say, minus 2 log x, the only difference is it's upside down. But it still crosses at 1, because log of 1 will be 0. We can't put negative numbers here because we don't want negatives, so it can only be positive. But, I mean, you can think about it like this. Like, if you had log 2x, you can actually just change that into, if you had log of 2x, you could change that into log 2 plus log x. So what's the effect of having the log 2 here in the graph? How does the graph change if you add a number to it? You know, if you have a quadratic, like x squared, but add a number to it, what happens to the graph? It raises up a unit. So the effect of having a number here is only to raise the graph up. Okay. Anyway, that's a little bit more advanced than what you need. For exam purposes, they only really ask you kind of these two situations, you know, like 2 log x or minus 2 log x, or 3 log x and minus 3 log x, that's all.
What time is this?
This one is at the 43 mark.
but you could have the negatives.
Yeah, you could. Yeah. I mean, they don't. In the exam, really, they actually only care about asking the student for log x. I mean, they could just throw in a number, 2 log x, same thing. You know. Okay, do you have this one written down? Yeah? So, I want you to start on these for a few minutes. So, we'll say the first and the last. First and last. I'm not. Could you get the light, please? Thank you.